Hello everyone, I am Abhishek Datta and you all are watching my YouTube channel Mathematics Made Easy. Today in this video, we are about to discuss about improper integrals. Now improper integral comes under the topic definite integral, and this video is particularly intended for students of BTech and BSc, that is for those who are studying engineering or who are studying honors course in mathematics. Now let me first start with the concept of a definite integral and then to classify this in two kinds, one proper integral and the other one improper integral. So as you all know, by definite integral what we mean, so a definite integral is of this form, that integration a to b fx dx. This is the form of a definite integral a to b fx dx. So here we have two limits, one lower limit or the inferior limit, and this one is the upper limit or the superior limit, and we are integrating the function fx with respect to x from a to b. That is, this is the domain of integration, a to b. As you all know, this we call the domain of integration, where fx is a function which is defined on the number line between the interval a to b. Now this definite integral is said to be a proper integral, a proper definite integral. Definite integrals are of two kinds, one is proper, the second one is improper. So when we call it a proper definite integral, so a proper definite integral, when these lower limits and upper limit, that is a and b, these constants are finite real numbers, that is the first condition. So number one, the first condition is both a and b must be finite real numbers. That is the first condition, both a and b must be finite real numbers. And secondly, the second condition, that fx, the function fx, that is the integrand function, the function over which the integration is being applied is known as the integrand function. So the integrand function fx must not have any point of infinite discontinuity, any point of infinite discontinuity in a less than equal to x less than equal to b. That is, in this interval a to b, in this closed interval, the integrand function must not have any point of infinite discontinuity. That is the second condition. If both the conditions hold, then this integral is said to be a definite integral of proper kind, that is a proper definite integral. Now what we mean by a point of infinite discontinuity, by this we mean that there must not exist any point between c and d, that is on the number line. If this is our real number a and this is our real number b, then this closed interval must not include any other real number c, or it may be a and b, c may be a and b also, or any point in between. So we must not have any such point c in the closed interval ab at which the value of fx tends to either plus infinity or minus infinity. If we have such a point c in the closed interval ab, such that fx at this point c tends to either plus infinite or minus infinite, that is f of c, fx at the point c, that is fc, functional value of fx at x equal to c, which is fc, if this tends to either plus infinity or minus infinity, then c is said to be a point of infinite discontinuity of fx. So there must not be any such point within a to b, within this closed interval a to b, at which fx tends to either plus infinity or minus infinity. That is the second condition. So if both the conditions holds, then this integral is said to be a proper definite integral. So naturally, improper definite integral occurs when either of these two conditions fails, either of these two, that is at least one of these two conditions when fails, then this is said to be an improper definite integral. So in case of an improper definite integral, either the lower limit or the upper limit or both lower and upper limits are infinite, they are not finite real numbers, they are infinite, or the function fx must have at least one point of infinite discontinuity within the range of integration a to b, then such integral is said to be an improper definite integral. So improper definite integral is when either of those two conditions does not hold. So our main discussion is about this type of integral here, that is improper definite integral. Now such integrals, improper definite integrals, can be classified into two types, type 1 and type 2. So such improper definite integral, we can classify them under two types. So let me explain you these two types and also their procedure, the procedure how to evaluate them. So improper integral, first we are discussing type 1. That is when we have integral a to b fx dx. If the first condition violates, that is either a tends to minus infinity or b tends to plus infinity, or both of them simultaneously tends to minus infinity and plus infinity, then this is said to be an improper integral of first type, that is type 1. So if a tends to minus infinity but b is finite, b is a finite real number but the lower limit tends to minus infinity, this can be one case. Or if a is finite but the superior limit, that is the upper limit b, tends to plus infinity, then also this is type 1 improper integral. Or we may have both the limits a and b simultaneously tending to infinite, that is if the lower limit tends to minus infinity and at the same time the upper limit tends to plus infinity, then also we call this an improper integral of type 1. So we have three cases under type 1 improper integral. Case 1, where the lower limit tends to minus infinity but the upper limit is finite. Case 2, when the upper limit tends to plus infinity but the lower limit is finite. And case 3, when both the lower and upper limits tends to minus infinity and plus infinity respectively. So in all the three cases we have an improper integral of type 1. So examples of such integrals are, say we have integral minus infinity to 2 x square dx. So this is type 1 improper integral under case 1, where the lower limit tends to minus infinity but the upper limit is finite. Or if we have integral 1 to infinity e to the power x dx, this is also an improper integral of type 1 which covers the case 2, that is the upper limit tends to plus infinity but the lower limit is finite. Or we may have integral minus infinity to plus infinity xs cube dx. So here both the inferior limit and the superior limit tends to minus infinity and plus infinity respectively. So this is improper integral of type 1 under case 3. Next is how to evaluate such improper integrals. So let us discuss the cases one by one. First let us discuss case 1, that is when the lower limit tends to minus infinity but the upper limit is finite. So when the lower limit tends to minus infinity but the upper limit is finite, that is we have an integral of the form say integral minus infinity to b fx dx. Minus infinity to b fx dx. So here as we see, this is an improper integral under case 1. Then here what we do, first we have to replace the lower limit by capital X, by a variable capital X, that is integral capital X to b fx dx. Mind that here this x, capital X is different from this small x. So we introduce a variable capital X, we replace the lower limit, that is minus infinity by capital X to b fx dx, and we apply a limit over this definite integral when capital X tends to minus infinity. Now if this limit exists, then we say that this improper integral is convergent. In other words, the improper integral exists, or we say the improper integral is convergent. Otherwise, if the limit does not exist, we say this improper integral is divergent. So this is the working procedure to evaluate type 1 improper integral under case 1. Similarly, when we have type 1 improper integral under case 2, so here we have the lower limit is a finite real number but the upper limit tends to infinity, that is integral a to infinite fx dx. Improper integrals of such kind, a to infinity fx dx. So here also we replace the upper limit by capital X. So we write this is equal to integral a to capital X fx dx, and we take limit over this when capital X tends to plus infinity. Again, if this limit exists, then we say that this improper integral is convergent. Otherwise, if the limit does not exist, we say this improper integral is divergent. And finally, type 1 improper integral under case 3, that is when both the lower and upper limits tends to minus infinity and plus infinity. So we have integral minus infinity to plus infinity fx dx. Then first we break the range of integration, that is minus infinity to infinity, into two halves. That is, if this is the number line, here is our minus infinity, this is the plus infinity, that is the extremities, and we take any arbitrary value, say c, any arbitrary real number c on the number line, and we break the range of integration, that is minus infinity to infinity, into two halves. One is from minus infinity to c and the next one from c to infinity. So then this integral is written as integral minus infinity to c fx dx plus integral c to plus infinity fx dx, where c is a real number, that is C belongs to the set capital R, set of real numbers. C is an arbitrary real number, but for particular cases we take C to be a fixed real number, that is for individual calculation C is said to be a fixed real value. You can take any numerical value also instead of C. You can take minus infinity to 0 plus 0 to infinity, or minus infinity to 5 plus 5 to infinity, any number will do. But it's better to deal with an alphabetical symbol C, because this is arbitrary then, minus infinity to C plus C to infinity. Now if you note carefully that this improper integral has been split up into two parts, where the first part covers under case 1, where the lower limit tends to minus infinity but the upper limit is finite, and the second part covers case 2, where the upper limit tends to plus infinity and the lower limit is finite. So then we apply the previous methods, that is here we replace the lower limit minus infinity by a variable x1 to C fx dx, and we apply limit over this as x1 tends to minus infinity, plus here also for the second one we replace the upper limit by x2, so it becomes C to x2 fx dx, and we apply limit over this as x2 tends to plus infinity. Mind that you cannot take x in either of, in both cases we cannot represent the variable by the same symbol, because here one tends to minus infinity, the second one tends to plus infinity. So we have to use two different symbols, x1 and x2, and if both the limits exist, then we say this improper integral is convergent. If at least one of them does not exist, we say this improper integral is divergent. So this is how to evaluate improper integrals of type 1. Let us now discuss how to evaluate improper integral of type 2. So in type 2 improper integral, the first condition holds, that is the lower limit and upper limit both are finite real numbers, but the function fx will have at least one point of infinite discontinuity within the interval a to b. So here also we have three cases. Say we have integral a to b dx upon x minus a whole square. Let us consider this improper integral a to b dx upon x minus a whole square. So as you see here, both the lower limit and the upper limit are finite real numbers a and b, but the integrand function fx, here fx is given by 1 upon x minus a whole square, that is fx, the integrand function over which the integration is being applied. So here we have 1 upon x minus a whole square, and as you can clearly see that fx tends to infinite as x tends to a, or in particular f of a is infinity. So a is the point of infinite discontinuity of fx, but note carefully that here a is the only point of infinite discontinuity of fx in a to b, because the denominator of fx becomes 0 only when x takes the value a. So here the lower limit is the only point of infinite discontinuity of fx. So this is improper integral of type 2, and this comes under case 1, that is when the inferior limit itself is the only point of infinite discontinuity of fx, then this comes under type 2 improper integral under case 1. Similarly, type 2 improper integral under case 2 becomes the case where the superior limit, that is the upper limit, becomes the only point of infinite discontinuity of fx. So if I just replace in the same example, if I replace a by b, that is integral a to b dx by x minus b whole square. So here it is clear that fx has the only point of infinite discontinuity at x equal to b, that is the superior limit itself is the only point of infinite discontinuity. This is the only point, mind that there is no other point in between a and b where the denominator of x vanishes. The denominator vanishes only at x equal to b. So this is case 2, when the upper limit is the only point of infinite discontinuity of the integrand function, and case 3, that when an interior point, that is a point in between a and b, becomes the point of infinite discontinuity of fx. Likewise, say if we consider the improper integral 1 to 3 dx by x minus 2 into x plus 4. So here as you can see fx is given by 1 upon x minus 2 into x plus 4, and fx tends to infinity at x equal to 2. You can say fx also tends to infinity at x equal to minus 4, but we are not interested in the point minus 4 because that is not covered within our range of integration. We are only interested at the points between 1 and 3 where fx will tend to plus or minus infinity, and here the point is 2 because 2 lies between 1 and 3, so it is an interior point of the interval. So here fx tends to infinite at an interior point of the interval 1 to 3. So this is type 2 improper integral case 3. So here also we have 3 cases, case 1, case 2 and case 3. Now how to evaluate these? Let us again discuss the cases one by one. So under case 1, when the inferior limit, that is the lower limit itself, is the only point of infinite discontinuity, that is also said to be a tumor point. That is when we have say integral a to b dx, or say in general let us write a to b fx dx, and let us consider that x equal to a is the only point of infinite discontinuity of fx. So such a point is said to be a tumor point. So if this is the interval a to b, so as if we have a tumor point at a, then what we do, we cut a certain portion of this interval. As we cut a portion to remove the tumor, so we cut a certain portion from this interval on the right hand side of a. We cannot cut any portion from the left hand side because the function is defined only between a and b. Outside a b the function is not defined at all. So to remove the tumor, we have to cut a certain portion from the right hand side of a, and say this length is epsilon. This length is denoted by epsilon. Epsilon is usually used to represent small lengths, small quantities. So this point becomes a plus epsilon. Then we covered the integration from the range a plus epsilon to b, because in this range there is no point of infinite discontinuity, because a was the only point of infinite discontinuity. So to remove this tumor, we cut a portion of length epsilon on the right hand side of a. So we take the integration as, the range of integration now becomes a plus epsilon to b fx dx, and then we apply limit over this integral when epsilon tends to 0 plus. So epsilon means this length, this small length epsilon. So as epsilon tends to 0 plus, that is this length becomes smaller and smaller, this point tends to the point a, that is this point becomes nearer and nearer to a. So practically we are covering the range a to b. So this is, if this limit exists, then we say this improper integral exists. But mind that here epsilon will tend to 0 plus. We should in particular mention 0 plus, that is epsilon is a very small, infinitesimal small positive quantity. If I say some constant tends to 0, it may tend to 0 from either of the sides, from negative side of the number line or also from the positive side. It may be slightly negative or slightly positive, but here epsilon will tend to 0 only from the right hand side, because epsilon being length, this denotes length between 2 points, so length or distance cannot be negative. So if epsilon has to be very small, that is if epsilon has to be very close to 0, it must tend 0 from the right hand side of the number line. So you must write epsilon tends to 0 plus in particular. So if this limit exists, then we say that this improper integral is convergent. Similarly, under case 2, when the upper limit, that is the superior limit, is the only point of infinite discontinuity of fx. So here we have a tumor at the point b. So as similar to the previous case, here we have a tumor at the point b. So we have to cut a certain portion around b. So we cut a portion from the left of b, because the function is not defined on the right. So here this point is b minus epsilon, where again this length is epsilon, and we take the integration from a to b minus epsilon, because there is no other point of infinite discontinuity, because b being the only point of infinite discontinuity. So we now consider the integration from a to b minus epsilon fx dx, and we consider limit over this integral as epsilon tends to 0 plus. Again epsilon will tend to 0 plus because epsilon denotes length, distance. Distance cannot be negative. So if this is very close to 0, it must be close from the right hand side of the number line. So if this limit exists, then this improper integral exists or convergent. It is said to be convergent. And in case 3, when we have an interior point as our tumor point. So here say x equal to c is a point of infinite discontinuity of fx. So this is the number line, here is our a, here is b, and say the interior point at this point c, fx becomes infinite. At the point c, the function fx becomes infinite. Then we have to cut a portion from either side of c because the point c lies in between. So the function is defined on both sides. So we have to cut a portion from either side of c now. So say one length is epsilon 1, the second length is epsilon 2. So here we have a point c minus epsilon 1 and here we have a point c plus epsilon 2. So we cover the integration from a to c minus epsilon 1 and then from c plus epsilon 2 to b. Because here as c is the interior point, we have to cut the portion from either side of c, but there is no such mandatory rule that the portions will be of equal length. So on one portion we may need to cut a length epsilon 1, the other portion we may need to cut a length epsilon 2. There is no mandatory rule that we have to cut equal amount from either side. We can cut unequal amounts. So we take a point c minus epsilon 1 on left hand side of c and a point c plus epsilon 2 on the right hand side of c. So the integration now becomes integral a to c minus epsilon 1 fx dx and limit over this as epsilon 1 tends to 0 plus, again plus, then integration c plus epsilon 2 to b fx dx and limit over this integral as epsilon 2 tends to 0 plus. If both the limits exist, then we say that this improper integral exists. If either of these fails, that is if at least one of these two limit fails, does not exist, then this improper integral also does not exist, or we say the improper integral is divergent. So this is the procedure to evaluate improper integral of type 2. And in this video, we shall confine our discussion up to here only. In my next video, I shall be dealing with some problems of improper integral and I shall illustrate all these procedures with some proper problems. So I hope this video is helpful to you. If you have any question or query, you can post them in the comment section. I will try my best to answer them. And if you like the video, please subscribe to my channel. It will help my channel to grow. And we shall meet soon in my next video. Thank you all for watching.